All right, we're going to continue our quest to compute derivatives. Just a reminder, we've talked about symbolic derivatives, those we know well from calculus, and we saw that they have their use for sure, but are a bit more limited in our applications because these expressions tend to grow exponentially. Finite differencing, easy to use, can be a default in many optimizers because it just needs a black box. But limited in their accuracy and scales with the number of design variables. Complex step was a cool idea. It also scales the number of design variables, but can uh, achieve machine precision. Today, we're going to talk about a new idea called algorithmic differentiation, which I'd say is the best of all the ideas we've talked about so far. This is a pretty powerful idea. It's sometimes also called automatic differentiation, but in both cases you'll hear the acronym AD. I prefer algorithmic just because it is automated, but it's not always so fully automatic. Sometimes you got to put a little bit of work in. Um, okay, so let's uh, let's motivate this. I'll motivate with this idea of dual numbers. It's well, I'll come back to this. This is not really how this is done, but just kind of to motivate this idea. So just to make a connection, we talked about complex numbers, right? We saw this is a complex number, right? And I squared is -1. And we saw that we could use those to help us predict a more accurate derivative. And essentially, the complex part of it was what we were using, this imaginary component was what we were using to carry a derivative. And that's nice because these are built into programming languages, and this was really cool. But we could take the next logical extension here that if we actually want to do derivatives, maybe we could create our own number. We'll call it a dual number. And epsilon we're going to define so that epsilon squared is 0. I'm just going to define this and call this a dual number. And then this is going to lead to this natural idea that the real part, if you will, is not really the real part, is primal part now, carries the function value as always, but this component is going to carry our derivative. So just as an example, we could do a Taylor series example like we have been doing. This is not exactly analogous to what we've been doing, but just an example. Let's say I do some epsilon. So this could be a plus b epsilon, but b is going to be 1 and a is just x here. If I do the Taylor series, it's going to be f of x. Let's just do 1d for now. F prime of x times epsilon plus f double prime of x times epsilon squared over 2 plus more terms. But we see we've got an epsilon squared, and of course, every higher term here is also going to have an epsilon squared. So all of these are just going to go to 0. And what we notice is that if I plug in this dual number here, I'm going to get back another dual number. And this dual number carries my function value, and in this part, the derivative. And in fact, we could keep chaining this forward. So for example, let's say I had two variable, or let's say I had two-step computation here. I first have some function, y is a function of x, and f is a function of y, and I want df dx, right? So I'm just going to do these as I would normally in a computation, just one line at a time. So if I plug in first for x, I'm going to plug in same thing that we did. I'm going to instead plug in a dual number, x plus epsilon. Okay, and if I do that, what's going to come out is just what we see above, y of x plus, this is going to be dy dx times epsilon, right? It's the same as above. And notice that this is not an approximation anymore, right? Like these are all gone. So I didn't have to truncate anything. This is going to be able to carry an exact derivative here. Now I've got a new number. This is a dual number, right? It's like an a plus b epsilon. And so I'm going to plug that into, oops, sorry, I put f of x. This should be f of y. This is a sequence of calculations. So I'm going to plug that into there. So let's say y is a plus b epsilon, but a in this case is just y and b is dy dx. So I would get, just following the same formula again, I would get f of y plus, really I get, I'd get df dy times b times epsilon because there's a b here. I didn't carry that through before because that was just one, but you could consider that as the one term, right? That you could lump it all together as a new variable and it just comes out. So in this case, um, this is f of y, and b in this case was this term, dy dx. It's just a number, but I could write it df dy times dy dx times epsilon. So you can see this kind of brings things forward in the chain rule. So I still have what I wanted here, f, and let me just be really explicit here. This is now f of y of x, right? Because uh, this whole term here is going here, and this whole term here is going here. Those are the a's and b's of that dual number. So I get what I wanted in this primal value, which is what we're used to, right? I plug in x, I get y, and then y goes into f. That's just, say, 2 lines of code. But here, I'm also getting the derivatives propagated. So I plugged in a 1 in front of the epsilon, I got out a dy dx. I put that dy dx in here, and that multiplied by df dy. So at the end, when I multiply these together, I get df dx, the number that I wanted, right? I wanted the function value, f of x, and its derivative, df dx. So again, this is maybe somewhat misleading. This is not how we actually implement this. We don't take a Taylor series of our functions, but it inspires this idea that rather than deal with these complex numbers, for example, we could just create our own object, if you will, that carries two values. One is going to be the function value that we're used to, but the other part is going to carry our derivative. And we're going to propagate that forward using the chain rule, so that by the time we get to the end of our function, we'll have our function value and the derivative propagated through together. So let's look at it another way. If that one didn't make sense, let's try looking at this a different way. So let's consider every operation in your computer. So you've got this big, long engineering program. It does tons of stuff, right? And there's loops, conditionals, all sorts of things. But at the end of the day, if we unravel everything that's happening, it's just a sequence of basic computations, right? We're multiplying things together. We're applying a trigonomic function. We're applying an exponential function. Even if we're doing more complicated things, right, like a solver or an integral or whatever, inside of that, it's just a bunch of sums and multiplications and things, right? So our long computer code is really just a sequence. This is how it's going to be broken down anyway, a sequence of these basic operations. So we could write it like this, right? Every basic operation we're going to call V. So operation I is going to be some function of everything that came before it. V1, V2, all the way to Vi minus 1. Okay, and that's just to say that some operation of my code just depends on everything that's before it. And this is quite general. We can have code, right, where things later or things before depend on things after because there's loops and things, but we're just going to unravel all the loops. At the end of the day, there's going to be some sequence that just moves forward. So this is general to say it this way. Okay, so we have all these operations, and as we break them down, they're all really basic things. And we know the derivative of all of these basic things. We don't know the derivative of this big complicated thing, but we know the derivative of adding two things together. We know the derivative of taking the cosine of some argument. We know the derivative of taking the exponential of some argument. And we also know how to apply the chain rule. So we can propagate these derivatives forward. We've got this basic operation. We take the derivative of just that operation. And now we've got this number that we're going to pass forward to the next operation. And via the chain rule, we're going to propagate that derivative forward. So we could write this mathematically like this. What I want at the end of the day is I want the derivative of my output, say Vi, with respect to some Vj. It might be V1, right? But it's one of these, right? It's, at the end of the day, it's going to be some X that I care about. And it may be this one, but it may be some other one. I don't know. So I want some derivative there. And so I'm gonna have to use the chain rule, right? So just to give you an example, let's say I had V4 is a function of V1, V2, V3. I have to use the chain rule, right? The derivative of V4 with respect to V1, for example, is going to be the partial of V4 with respect to V3 times dV3 dV1 plus the partial of V4 with respect to V2 times V2 dV1 plus the partial of V4 with respect to V1, right? So if this is a bit, if you haven't seen this for a while, I'd encourage you again, look in the appendix at the chain rules and things. But let me just write this generally. That was just a specific case. You can see there's going to be this sum. So I'm going to have to do a summation of the partial of VI. I'm just write them. I'm just going to keep them all lowercase. VI with respect to VK times the derivative of VK with respect to VJ, right? And this is not a cancellation, but it helps to check, right? These Ks would cancel, so to speak, and I've got an I on the top, J on the bottom. So it looks good. And the summation is occurring over the common index K. So that goes from K equals J to I minus 1, right? So if I want the derivative with respect to V3, for example, I only need to, it doesn't depend on 1 and 2, so I only need to start the sum at 3, and I would end at I minus 1 because there's nothing else after that. Okay, so this is a formula that we could use to compute derivatives via the chain rule. And just as a matter of notation, this isn't anything new. This is not some new math. It's just going to simplify our expressions. We're going to just call VI dot. That's just going to be this total derivative. Notice there's our partials versus total derivatives. dVi, dVj. That's just what we're going to call this. Okay, just so I don't have to write a bunch of things. So anytime we have this V dot, that's just going to be a total derivative instead of a partial derivative. Okay, so that may feel a bit abstract. Let's do an example. This is basically the example I just did, but we'll put some numbers in it. Let's say that you have 4 variables. Okay, that's in your entire code, just a really simple thing. You just have 4 variables, V1 through V4. And let's say, oops, the thing that, let's say X is V1 and V1, and F is V4. And what we want is df dx. So in other words, we want dv4 dv1. Why do I keep writing I? 1. Okay, so it's a very simple code. It just has 4 operations. So what we do is we have this procedure. We're going to say, okay, v1 dot. Remember, that's just going to be dv1 dv1. So this is just going to be 1. So we just start with that first one. We're just going to loop through the sum here. V2 dot is going to be the partial of V2 with respect to V1 times V1 dot. Okay. And notice that's it, because V2 only depends on V1. There's nothing else, right? V1 only depends on itself. There's nothing else because these are ordered. Right? We've listed these in order of what they appear in our code. Now V3, it can depend on V2 and V1. So it's going to be the partial of V3 respect to V2 times V2 dot plus the partial of V3 respect to V1 times V1 dot. And then so on, we'll do the last one, V4 dot. That's the partial of V4 with respect to, and it depends on 3 or 1, 2, and 3. I guess I've been doing it in this backwards order, which is fine. Doesn't matter which order. Start with 3, and then I'll go down to 2, and then to 1. Okay, and notice that at every line, we don't have this big sort of symbolic, this is not a different than symbolic differentiation, or sorry, this is very different than symbolic differentiation. We're not carrying some symbols forward, we're carrying numbers. So here, when we have V1 dot, it's 1, it's done. That's just a number we can plug in. So every time we use V1 later, we just plug that number in. Similarly, once we get V2 dot, you know, we can just keep reusing it. And then once we get V3 dot, we just use it. So those are numbers that we compute. And notice that each line just depends on things that we computed in previous lines, these total derivatives. Then the new things at each line are only partial derivatives. These are not total derivatives, they're just partial derivatives. So all it says is, how does this one operation, V4, depend on my other variables? So I only need to do one very simple derivative. This would be like, say, this operation could be the sine. Maybe V4 is equal to the sine of V3 or the cosine of V3. I can figure out these derivatives very easily. right? And my computer can do that automatically. And then I just plug in those numbers, multiply by these other numbers I already have, and I get a new total derivative, and that just keeps marching down. So I know this can be a bit confusing. I'll try to illustrate with another example, but just think of it, if it may help just to think about conceptually what's going on. Again, I would think of your code, right? It's this complicated thing. It's got this long bunch of stuff, but at the end of the day, it's just a bunch of really simple things. And each thing, say you multiply two numbers together, we know what the derivative is for that. We can just look that up, right? And then we can apply the chain rule to propagate that forward to the next operation, the next operation, the next operation. Super tedious to do yourself, but something that a computer is great at doing. In fact, it's already basically doing that as you're evaluating your function, right? You're evaluating a function, propagating that result to the next operation, and to the next, and to the next. That's what we do in code, right? Is we're chaining a sequence of operations together. We're doing the same thing now, only with the derivative portion of our function. So let's do another example with more numbers. Maybe this would help. This is a function we saw before when we did a simple review of what a Jacobian looks like. So it's a function with two inputs, x1, x2, and two outputs, f1 and f2. And we could draw it like this little diagram here, if that helps you think of it. We're basically moving forward from inputs to outputs. So this method we're using is called the forward mode. We'll talk about, there is a reverse mode, and we'll talk about that next time, but we don't have to worry about that for now. So you can see this is kind of a pictorial example of these operations. We could take x1. We need to multiply it by x2. So we take x1 and x2 as inputs. We do a multiplication. That's one operation, right? And that occurs in two places. We take x1 and we use the sign operator, right? That's this part here. We take that result of the sign operation and these multiplied numbers here, and we add them together. That's another operation. And that gives us f1, for example. So this is just a pictorial example. Let's write it out as if this was like, this could be a sequence of operations in the code. So v1 is just x1. We just set it to x1. That's a simple operation. And the second operation is really simple too. We're just setting it to the second input. Our third operation is we're going to multiply these together. Okay. No, there's not really a specific order. We could have done the sign first, or we could have squared. It doesn't matter. We could do this in any order that seems to make sense, as long as it's consistent with the order operations. And notice, of course, that every number will always depend only on things that have happened before. We have to do it at least in order, the things that it depends on previous values. So V4 now can depend on things that are before, and we'll choose to do this, the sign. So this is the sign of V1. Okay, that's taking care of this part. The next operation we're going to do is we're going to add those two together. So we want to add, we multiplied x1 and x2 and we took the sign. So we can add v3 and v4 here. Okay, that's another operation. And then that gives us f1, right? So incidentally, this is f1. V6, so we've already got x1 times x2. This part, that was this. We need an x2 squared, so that's going to be our next operation. That's v2 squared. And then we need to add it to v3, so that's our last operation here. v7 is v3 plus v6. So again, we haven't done anything with derivatives yet, just thinking about how we could how a computer might break things down, right? Just a sequence of elementary operations. Okay, there's f2. All right, so we're going to use our forward rule here, and we want to take these derivatives. Okay, so we are going to take derivatives with respect to x1. We can only do one at a time. So in the forward mode, we're going to do a derivative with respect to one input at a time. So we're going to take derivatives with respect to x1. That's what we're going to do here. So when I say v1 dot, that means the derivative of v1 with respect to v1. And of course, that's 1. v2 dot is the derivative of v2 with respect to x1. So let's again write the dots so we can remember. In our case, right here, different colors so it doesn't clash. V dot I is going to be dvi dt. v1. And it's only one in this case because we're doing the derivatives with respect to x1. We can only do one at a time. So v2 dot is 0. The derivative of v2 with respect to v1 is 0. Okay, so that's basically just initialization. So v3, this is where we start to apply this, well, really this one, this summation rule here. Okay, so this is the chain rule. It's going to be the partial of v3, and it only depends on 2 and 1, right? So it's the partial of v3 with respect to v1 times v1 dot, plus the partial of v3 with respect to v2 times v2 dot. Okay, and notice v1 dot, v2 dot, those are numbers I already know. They're always going to depend on things that I computed before. So all I have to do in this line is to take derivatives of this single operation. This operation is a multiplication. Okay, so I can have some function that knows how to do that, right? So the derivative, and we'll see that in a second. The derivative of v3 with respect to v1, that's just v2, right? That's just a number. So this is a number, this is a number, it's going to be v1. So I'm going to get out a number here. In this case, it happens to be 2, for example. And this is an example in the book if you want to look in a little more detail. v4 dot, same thing. It's going to be the partial of v4 with respect to v1 times v1 dot plus the partial of v4 with respect to v2 times v2 dot plus, and it goes on, right? We go with respect to v2, with respect to v3, but in this case, it only depends on v1, so those are all 0. So again, every line, what I'm going to be doing the same thing. I'm going to be reusing derivatives that I already have, and I just need to take a derivative of this one line, this one operation. So the derivative of sine is going to be the cosine of v1. So that's what I'd plug in here, multiply by numbers I already have, and now I've got a new total derivative. I march my way through. Okay, so again, this is in the book, so you can take a look in a little more detail. I'm going to show you some examples in code, see if maybe looking at a third way might help here. Before I do that, let's talk about it in a conceptual way. So remember how we talked about this idea of a dual number, and the dual number was something we were going to define. We wanted it to be basically like a complex number, right? A complex number has two numbers basically, right? Or not basically, it does. It's got a real and an imaginary part, and our dual number is going to have the same thing. Whereas the imaginary number is already built in, we're going to create our own number, right? We're going to call it a dual number. If you're familiar with object-oriented programming, this may be familiar. If not, it's okay. You don't have to worry about it. You could just think about this idea. So imagine this, right? Like when I call the sine function, for example, in the computer, there actually is not just one sine function. There are potentially many sine functions and many of every type of mathematical function that are going to depend on the type of x. So if x is just a floating point number, it's going to call one thing. If I put in a complex number, for example, then it needs to call something else, right? It's still the sine, but what it computes is a little different. So by the same token, I can define now my own type called the dual type, and I can define what sine should do when it calls the dual type. So I can overload, this is called overloading a function. And this is what's happening already for all of these mathematical functions. They're overloaded, meaning there are multiple definitions with the same name, and they have different operations depending on the inputs that are passed in, the type of the inputs that are passed in. So we're going to define our own object here. We're going to define this object, and we're going to call it dual, okay? This is my pseudocode here. And it's going to have two numbers. So if this was a complex number, we might say, oh, it has a real and an imaginary part. We could just call it as this object that contains two numbers. But in our case, we're going to say it has the value and the derivative. And there's nothing special about those names. That's just what I'm going to call it here. We could call it other things. You call it primal and dual or whatever you want. Okay, so now I could create a number. I could say x is, let's say it was complex. I might say I had a complex number that was 1, 2, and that would represent 1 plus 2i, for example, right? In my case, since I defined my new type, I'm just going to call this dual, and I could give it, numbers 2. Okay, so I can define this type. Now I need to overload my function. So if I call the sine function, if I call the sine of, uh, let's say some dual number here, um, we'll just call it sine of x, uh, where x is a dual, right? So again, remember, the sine function is going to be different depending on what's in there. So if I had a complex number, it actually calls something else. I just made up this dual number, so my computer doesn't know what to do with it. So I need to define this for it. So I'm going to define what should be returned. And I put in a dual number and I want to get a dual number out. So I'm going to create a new dual number. Okay. So it's going to have a value and a derivative. So what should I place in the value? So think about that for a second. What do I want to pass through as the value of this operation? Well, what I want to do is I want it to return the sine of x, right? The sine of the value in x. So I want the sine of x dot value, right? Because x has both a value and a derivative. So I just want just the value portion to go forward. So this would be operate exactly the same as it always does. Because remember, the first part of my dual number is just containing the function value. This part is the derivative. So now I got to deal with the derivative part. Okay, so what should I put there? Take a moment and think about that. What do you think I should put? Well, the derivative sign is the cosine, so I could put the cosine of the value. And by the chain rule, right, it's the cosine of x times the derivative of x. But I know what the derivative of x is. I've got it. It's that derivative term that I've been carrying. So now I plugged in some dual number here for x, and I get a new dual number out where this first value just keeps the function value, and the second one is propagating my derivatives via the chain rule. Okay, so you could see where this is going, perhaps, that for this to work, right, someone needs to define all of these operations, right, for all these sort of functions that we might use. They're all really basic things, but once I've defined them, I can write this very generic code. And instead of just giving, I can write the same code that I would normally write, but now instead of just giving, say, a floating point number, x equals 0.1, I can give it this dual number, and it's not only going to evaluate the function, it will also evaluate the derivatives for me alongside. We're going to write our own just as a learning exercise to kind of get a feel for how this works, and we'll do that in class, and I'll talk about that in a second. But in general, you wouldn't do that, right? There are libraries, packages for this that you just download and use, where someone has gone to the work of doing these and making them efficient and dealing with some subtleties that we won't get into here. But it's worth writing your own small one just to kind of get a feel for how these work. Okay, so let me do a demo of just exactly what I just talked about here. I'm going to change what I'm sharing here. I'm actually just going to do this in Julia because it'll be the shortest syntax, but don't worry about the syntax per se. Focus on the idea here. So let's say x is 0.1. We already know that we can evaluate the sine of x, of course, and that just does what we're used to doing. I could also say, well, what if x equals 0.1 plus 1 IM, right? This is an imaginary number, okay? I don't have to call some other function. I could, for example, in my programming language, say, let's make a new function that's called sine complex, right? But it doesn't do that. It's just overloaded so that the same code will work. It's not calling the same function, right? The sine for this one that takes a floating point versus the sine that takes a complex. They're different functions, but we've overloaded them. So they have the same name. And so if I want to change my code from real to complex, I didn't have to rewrite all my code and change all my reals or all, I didn't have to change all my sines to sine complex and all that. That's just a convenience here. So what I want to do is I want to define this dual type. I'm going to create one. And don't worry about the syntax. In Julia, we call it a struct here. I'm just going to name it dual. And I'm going to say it has a value and a derivative, just like we said. Okay, so now I can create a dual number, something like this. And, if I call the sine for it, it's not going to know what to do. It's like, I don't know what to do with a sine when you pass in a dual. I have to define that. So I'm going to define it exactly like we just said. I'm going to say, okay, I want to define the sign where x is a dual. That syntax just means if x is a dual number, call this function. So just like we said, I'm going to create a new dual number, and I want to pass in the sign of the value of x, and the derivative portion is going to be the cosine of the value times the chain rule. Take the derivative of the inside, which is just that derivative portion. So I'm going to return this new dual number. And I actually have to do one more thing just to overload. Don't worry about it, it's just a syntax thing. I just have to say, this is coming from base, just overload this function. So now I've redefined this function. So now x is my dual number. If I call the sign of x, notice it gives me a new dual number. And hopefully, if I've done this right, this is going to be the sign of 0.1, and this is going to be the cosine of 0.1, the derivative of the function at 0.1. So let's just check that, sine of 0.1. I'm just going to evaluate them both side by side. And indeed, it looks like I've got it in there exact, right? I get the function value exactly. I get the derivative exactly. Right, so remember, this is the x value, so it's 0.1 in both cases. This 1 here, we always start with 1. This is just telling me that this is the derivative with respect to x. We'll see in a second that if x is like a vector, then I'm going to have a vector of like 1 and a bunch of zeros, for example. They could have numbers that are not 1 with a vector, but that would be like for a directional derivative or something. Okay, so let's maybe make this a little more complicated and maybe see a difference between symbolic differentiation, because this on the surface seems like that, right? And it is related, but it's not the same. So let's say, for example, I want to do the sine of the sine of the sine of x, just because that sounds fun. All right, so that just worked, right? Hopefully. So this part here should be the sine of the sine of the sine of 0.1. That's what I want it to be. And indeed it is. This number is exactly the same as this number, so it didn't touch my function value. That's good. This should be the derivative of this expression with respect to x evaluated at 0.1. So that's kind of a pain. Symbolically, it looks like this. The cosine, let's see, cosine of sine of, got to do the chain rule here, of 0.1 times the derivative of the inside, which is going to be the cosine of the sine of 0.1 times the derivative of that inside, cosine of 0.1. Yeah, and indeed this number is exactly the same as this number. It's the last decimal place there, right? So exact derivative. But notice the difference here. This symbolic expression, let's say I just keep nesting this, right? I do 10 signs, like this is in a loop. This symbolic expression is just going to keep exploding, right? Via this chain rule, it gets really, really big. But it's not the case here with the AD. So let's say I do the sine of x. That gives me a new dual number. And I take the sine of that answer, a new number, sine of that answer, new number. And that's the derivative that I'm after, right? The sine of the sine of the sine of the function. So at every time, we just have numbers. We're not propagating these big symbolic things where you take derivatives and you got to traverse all the way back via the chain rule. We're just evaluating this line that always depends on, just like you evaluate a function, it just depends on things that happened before. As long as we use numbers, right, this derivative just depends on things that happened before. And so we just can very easily just do, a few extra or few derivatives, that whatever this function depends on, partial derivatives, and multiply through. It's really not that different, not too different from what's happening when you do a function. Imagine like you took your code, right, and it's got a sequence of these simple operations, and you tried to write that as one big, huge function and become really, really big. And now you take the derivative of that and just becomes crazy, right? In this case with the numbers, right, it's just we evaluate a number, we evaluate the next number, and we just throw that other stuff away. We don't even care about what's back there, right? Because as we evaluate the function, we're just propagating a number forward. We're not saving these big, long expressions. Same with the derivative. We evaluate the derivative, it's a number. We're going to step forward to the next operation. We just have numbers. We're just propagating numbers forward, not symbolic expressions. We are using symbolic derivatives at each little operation, right? Somebody's had to define that, just like we define that here. That's what this line was. Someone had to define this. In this case, we did. We defined that the symbolic derivative of sine was cosine. That means that each time it knows how to propagate things via the chain rule. But that's just happening with a number, a line at a time, just like as in a function value. Okay, let me give you one last demo here, and I'm actually gonna do this one in MATLAB here. So let's switch to another screen. Let's see, where is that? MATLAB. Okay, so I did the same thing in MATLAB, and we're gonna do this in class. If you're not in class, I will post these on our our GitHub repo that has resources for the book. I'll post some starter files, and we're going to use the same function we used in complex step. Remember that little 1D function? It had like an exponential and sine cubed and so on. We're going to try to use AD, algorithmic differentiation, on that simple function. And you're going to write your own. Again, as we're going to write our own to learn how to do it, this is not what you should be doing in general, right? If you want to do these on your homework or in your project, you should use an actual package. This is just to help you kind of understand what's going on. So we're going to write our own in class. And if you're not there in class, like I said, go to those resources to try it yourself. But here's an example of that. In MATLAB, same idea. I define a dual. It's got a value. It's got a derivative. I construct it. And here's that sine, right? Same thing. I have a sine. The derivative is the cosine times the chain rule, right? And I've defined a bunch of other things, for example. But what I wanted to show you was not that. I want to show you this example where we're looking at a vector, right? This is a function that has has multiple components, not just one. So this is a very simple function. It's a linear function. I did that because we can pick off the derivatives by inspection, right? The derivative of f with respect to x1 is just 1. The derivative of f with respect to x2 is just 2. The derivative with respect to x3 is just 3, right? It's just linear. So very simple. And if I put in 2, 2, 2, I just get 12. That's all I'm doing here. But I defined this dual type. I called it my dual here. So I can use that. I'm going to define a dual. And my dual takes x. And so x is now a vector. And now before, when we started, we put just a 1. But I can't put a 1 now. I need to put a vector. And I'm going to put 1, 0, 0. Okay. So remember, before we start with the 1, and maybe you were confused, like, why did we have 1? Remember, we had a 0.1 for this part in the sign, and then we had a 1 here. Well, the 1 means I want a derivative with respect to x1, and these are all 0. So before it was just 1 because we just had just a scalar. So what this should give me is it should still give me 12 for the function value, and the derivative part should give me 1. So let's see what happens. I didn't even evaluate it. I just created the dual. I need to evaluate my function. And indeed, it says the value is 12 and the derivative is 1. So if I want the derivative of f with respect to x2, I need to change this input vector to be 0, 1, 0. And indeed, I get the function value 12, and the derivative with respect to x2 is 2, right? This coefficient here. And finally, if I wanted the derivative with respect to x3, I get 3 as expected. So almost always it's going to be a 1 and a bunch of zeros because we're getting the derivative with respect to that input. Sometimes you could have numbers in more than one place, like if you want to do a directional derivative, right? That'd be a vector in some non-coordinate aligned direction. But most commonly, we want the derivatives with respect to each of our x components. So notice that we still have the same kind of challenge we had in forward difference and in complex step, where this is going to scale with the number of inputs. As I have more design variables, I need to evaluate this function nx times. So again, if I've got 50 design variables, I'm going to have to do this 50 times. So it has the same complexity as a forward difference complex step. In practice, it generally scales better though. That sort of constant in the scaling is usually better, in part because it's not a total black box like complex step and finite difference. If you remember, we operated on the entire function after it was evaluated, whereas these dual numbers, kind of propagating numbers as we go. And so there tends to be a lot of reuse that sometimes, right? It depends, but it tends to be more efficient. Um, but the other real power of algorithmic differentiation, or AD, that we'll talk about next time, is that there's actually a reverse mode too. Unlike forward diff and complex step, where there's no such thing, we can do this in a forward mode or a reverse mode, and we'll see that next time. So there's a few more details to discuss here. So next time we'll talk about some of these forward and reverse. We'll talk about a few different ways to do AD. What we've done here is called operator overloading. Remember, because we overloaded these functions, we created new versions with the same name. But there's another way to do that, and we'll talk about that next time as well. We'll see you then.